So we are in generalized linear models with examples in R, that book right there. Chapter 3, question 3.13. Okay. So we are returning to a data set and model that was used in problem 215 from the last chapter, using the data set flowers, and then we're going to do some stuff with it. So first we need to install and load the GLM's data package. I've already installed it here, so I'm just going to comment that out. But run that, and we'll get just the first 6 rows here of the data frame. Okay, so we have variables flower, light, and timing. So in the problem 215, 2 models were actually presented, just an additive model and one that had an interaction between the other 2 variables, light and timing here. So I'm gonna do this problem for both of these. Okay, so I run the model, and the first thing that we're supposed to do is to perform a diagnostic analysis on the fitted linear regression model. Okay, so this kind of question is always just a little bit too open-ended, because we could, like, how deep do we want to go with the diagnostic analysis? But at least a good first step is always just to use the plot function on the different models, in which case we get, so here's the first 4 here are the first model, just the additive model. And so we can kind of begin to assess the fit here in different ways. So a few ways that we might do this is to look at how well the QQ plot is capturing the data. It looks like it's doing a decent job. We can try to see if the residuals compared to the fitted values are more or less homogeneously dispersed, and that seems to be the case. The standardized residuals over fitted values kind of gives you similar information. And then also we can look for highly influential points or even possibly outliers with the residuals versus leverage here. So as we go further and further to the right, we get more and more leverage. In other words, these are observations that have the potential to exert a lot of influence over the fit of the model. Well, anyway, so that's a good first stab at diagnosing our analysis. So that's as far as I'll go with this one. But because part 2 is we're meant to identify any influential observations or outliers. Okay. So really, maybe graphically, the way that we might do this, or the plot that we might refer to, is this bottom right one, looking for, well, highly influential observations. And this generated plot, one way that it tries to show you highly influential observations is you can't really see it here, but is to give you Cook's distance, and it kind of gives you these different thresholds, and only one of them is here. And observations that are falling outside of this threshold might be considered to be highly influential. So it doesn't really seem that there are many highly influential observations here. But just to kind of look at this, I thought that maybe we would kind of assign some numbers to our different observations. And so what I've done is I've done a couple of things. So one is, for every one of the points in this plot up here, well, really I'm talking about this plot and this plot. But for each of those points, I have found the standardized residual. So I found the x coordinate for each of the observations, as well as the leverage, okay, and also Cook's distance, okay. And so then I am putting these into a data frame, and so I've made this variable called distance, which is basically the distance of each of these points to 0, 0, right? So no leverage and no residual, okay? And so what I've done is I've just taken it's called the Euclidean distance. So I've just taken the distance of the leverage squared plus the value of the standardized residual squared, and then taken the square root of that sum, and that gives you kind of the linear distance from the origin to whatever that point is. And so bigger values are going to be more influential. But we can also kind of look at the influence of each variable just by using Cook's distance. Okay, and here I'm ranking the Cook's distances for each observation. I've done that for both models here. So we'll just look at one, but you can certainly look at both of these, on your own time here. Let this run. Okay, so I'm just looking at the additive model here. Okay, and so what we see is that that the observations that have a large distance from the origin in terms of leverage and standardized residuals, they are here and they're ranked according to that. Okay, so and I called that distance. Okay, so you see that these distances are going from greatest to least here. So this is distance from the origin, again, in terms of this plot right here. Okay, and then I've also listed the Cook's the Cook distance. Okay, I probably could have found better naming conventions here, but I've also put the Cook's distances in here and the rank of the Cook distance. Okay, and so you'll notice that that the greatest, Euclidean distance happens to be the greatest Cook's distance, which is the greatest, which I've assigned a value of 1, 2, and you see that roughly Cook's distances are more or less, aligning with this Euclidean distance here in terms of rank. So anyway, so as far as outlier observations, this book takes a different philosophical stance than I do in terms of in terms of outliers, because I think that really an outlier is a little bit of a subjective call. Like you might apply hard and fast rules to it. You might apply hard and fast rules to it, and maybe it's just simply something with a Cook's distance that is, exceeds some arbitrary threshold or something like that. But really, there does not seem to be any majorly outlying observations here. Anyway, okay, and finally, the last part, we're meant to interpret the final model, and I really dislike these kinds of questions, these very vague questions. But just predicated on what the book has asked for when it's asked for this in the past, it's almost a tautological answer, which is, the interpretation is, it's always the outcome is some linear combination of the predictors. I mean, that's just what it is. So yeah, I kind of struggle to give a better answer for those types of questions. But anyway, we will call that good here.